All right, welcome to The Explainer. Today, we're going to talk about a world that, well, it goes way beyond simple yes or no answers. A world beyond just plain true and false. We are diving headfirst into the really fascinating realm of many valued logics. So let's just jump right in with a pretty big question. Think about it for a second. Is everything in the world either completely true or completely false? Is a statement like it's warm outside, is that absolutely 100% true or false? Or maybe, does the truth kind of depend on degrees? Yeah, that question right there, it challenges the very foundation of how we're taught to think about logic. Okay, so here's a really great way to picture this. The classical logic we all learn, the standard stuff, it's basically like a light switch. It's either on, which is true, or it's off, false. Simple, right? But many valued logic, that's way more like a dimmer switch. It gives you all these shades in between. It allows for a whole spectrum of possibilities, all those different degrees of truth. So, what does it actually mean to build a whole system of reasoning on that dimmer switch idea instead of just a simple toggle? Well, let's find out. Let's step right into this world of many values and see what happens when we start to formally introduce those shades of gray. The core idea here is at the same time both really simple and totally revolutionary. Many valued logics, or MVLs for short, are just logic systems that intentionally move past that strict binary rule of just true and false. And how do they do it? Simple. They introduce more truth values. Maybe just one extra one, giving you three total, or four, or get this, even an infinite number of them. And believe me, there's a huge variety of these things out there. Some systems are pretty straightforward. They just add a few extra truth states. But then you have others, like the pioneering logics from Lukasiewicz and Gödel, that introduce a whole infinite spectrum of values. A lot of these ideas fall under this broader category you might have heard of called fuzzy logic, which is just this incredibly powerful concept designed to handle all the ambiguity of the real world. It does this by assigning truth values anywhere on a scale from 0 to 1. But as you can probably imagine, this whole dimmer switch model creates a brand new and pretty massive problem. See, all the traditional tools that logicians use for proving things, they were all built for that black and white on or off world. The moment you introduce shades of gray, well, those tools just start to break. Really think about it. The entire machinery of logical proof, that whole step-by-step process of figuring out new truths from old ones, it was designed from the ground up for a world with only two options. So, what happens when that's just not the case anymore? How can you actually be sure of anything you prove? And yeah, the old rules really, really do break. I'm talking about foundational methods for proving things, like these superstructured systems called Jensen systems. They were all built on that light switch principle. Their entire existence is based on the assumption that every single statement has to be either true or false, period. In a many-valued world, that core assumption just vanishes. And when it does, the whole system pretty much collapses. But here's the cool part. This problem didn't stop the logicians, not at all. In fact, it did the opposite. It sparked this incredible wave of ingenuity, and it led to the development of a whole new toolkit designed from scratch specifically for proving things in these new expanded logical universes. So, the logicians got creative. They came up with some incredibly clever solutions. We're going to touch on three of the most important ones. First, a way to basically tag formulas with their truth value. Second, a new method for totally restructuring proofs. And third, a really powerful technique for linking different lines of reasoning together. Okay, so this first tool is actually elegantly simple. It's called a signed formula. So instead of just dealing with a formula, let's call it A, you actually pair it with a specific truth value. It's literally like putting a little label on it that says, okay, for this part of the proof, we are considering the case where formula A has this exact degree of truth. And that simple little tag, it has some seriously profound consequences. It's what allows logicians to build these really elegant proof systems that can systematically explore every single possibility. It's almost like a branching tree of logic. And what that does is make it incredibly efficient to study the structure of entire families of many valued logics all at the same time. All right, on to technique number 2. First, let's think about the basic structure of a classical, old-school proof. You can pretty much picture it as two columns on a piece of paper. On the left side, you've got your assumptions, all the stuff you know is true. And on the right, you have your conclusions, the things that follow from those assumptions. It's a nice, neat, two-sided world.
But as you can guess, in a many-valued world, that simple two-column structure, it's just not going to cut it. So what did logicians do? They expanded it dramatically. They created what's called a many-sided sequent, which can have multiple columns. Each column can represent a different possible truth value. It basically gives you a dedicated spot to sort all your formulas based on their exact degree of truth.
Okay, and for the really tricky logics, the ones that resist even these cool new methods, there's a third, even more powerful tool. It's called the hypersequent. Now, the best way to think of this is like a whole collection of individual proofs that you consider all at the same time, like they're all running in parallel. It adds a whole new dimension, a whole new layer to the structure of a proof. And this technique, this hypersequent idea, it turned out to be the master key. This is what finally unlocked the proof methods for some of the most important and seriously complex systems out there. I'm talking about Gödel and Lukasiewicz logics, the very systems that form the bedrock of modern fuzzy logic. So, okay, this is a super fascinating theoretical puzzle, right? And the solutions are just incredibly clever. But let's bring it back down to earth. What are the actual real-world implications of all this? Of thinking beyond just true and false? Why should any of this matter to you?
Well, the impact is huge, absolutely massive. These many-valued logics are the foundation for fuzzy logic, and that's a technology that is used everywhere. We're talking about everything from the anti-lock brakes in your car to the advanced AI systems that have to make sense of uncertain or incomplete information. They are absolutely essential tools in modern computer science, philosophy, and artificial intelligence. They're what help us build smarter, more flexible, and more adaptable technology.
And this really brings us to the crucial takeaway from all this. The very moment we decided to move beyond that simple binary of true and false, we were forced to reinvent the very tools we use for reasoning itself. It wasn't just a small tweak, it required a fundamental, ground-up shift in our entire deductive machinery. And so that leaves us with a final and I think pretty provocative thought. We tend to think of logic as this rigid, ancient, unchanging set of rules, right? But what this whole journey shows us is that it's actually a dynamic, creative, and evolving field. So, if something as basic, as fundamental as true or false can be so radically reimagined, what other core concepts that we just take for granted every day are out there just waiting to be completely reinvented?